Hello and welcome back to my channel. Today we'll be talking about efficiency. So what really is efficiency and how is it related to our real world? Well, efficiency is basically just, the ratio of useful energy out to energy in. So it's really just an amount of energy in over the amount of energy out. And with this, we can calculate the efficiency of a system or something that we have. How is this really used? In your homes, you may, if you have an older home, you may have a radiator. And sometimes back in the day, they used to be really inefficient. They had like 80% or 75% or sometimes even 60% efficiency. And that would cause a lot of energy to be wasted. Nowadays, they're a lot more efficient. Even with our computers right now, if your computer maybe takes in a lot of energy, but the energy out is less, you have a less efficient device. You want your amount or percentage of your efficiency to be high because you don't really want to waste energy. So now that we understand that basic concept of where efficiency is really used, let's find out the equation for what efficiency is. So the equation for efficiency is simple. It's really just EFF is equal to E out divided by E in times by 100%. So whatever our energy out, we have to divide that by our energy in and multiply that by 100%, and we will get our efficiency for that particular system or device. So let's look at a few questions and maybe a little more examples of where efficiency and energy is really used. Okay, now let's take a look at some questions and try to use what we learned and apply it to solve these questions. So it says, a firefly's body transforms chemical energy into radiant energy to glow. What is a firefly's efficiency if its body transforms 4.13 joules of energy into 3.63 joules of radiant energy? So let's get into our given. We know that our energy in is going to be 4.13 joules. How did I really know that? Well, he has 4.13 of he uses 4.13 joules to glow. So he has an energy in of 4.13, and then he gets out to glow. He gets an energy of 3.63. So our energy out is equal to 3.63 joules. Now that we have that, we can go into our required to find, and we're looking for our efficiency. So we can go into our analysis. We know that efficiency is equal to E in over E out times 100%. Pardon me, this is the reverse, E out over E in over E in. And we're going to multiply that with 100, and we already have our E out and E in, so we can just go straight into our answer. So our E out is 63 joules divided by our E out, divided by E in, 4.13 joules, and multiply that by 100%. Because efficiency, it's always in percentage. We don't really have units for efficiency because it's more a percentage. So up here you can also write there's no units for efficiency. It's a percentage. So now that we have that, we can just go ahead and plug this into our calculator. We should get, 3.63 divided by 4.13 multiplied by 100 you get an efficiency of 87.89%. Round off to 3 significant digits because there's 3 in all of those. So 87.9% efficiency. So EFF is equal to 87.9% efficiency. So that is our total efficiency for this firefly. So now let's look at the next question. It's similar, but there's a little more thinking involved. So what is the efficiency of a rope in a pulley system if the painter uses 1.3 kilojoules of mechanical energy to pull on a rope and lift a 20 kilogram paint bucket at a constant speed to a height of 7.5 meters above the ground? Okay, so we already know our efficiency or energy in. Our energy in is 1.93 kilojoules. We're already given our energy in. So we know the mass of the paint bucket to be 20.0 kilograms. Okay, we got that. We know that the height is equal to 7.5 meters, and the velocity is just constant. So there's no really acceleration that's going on. We always know what gravity is, 9.80 meters per second squared, and are required to find, we're looking for our efficiency, right? So what are we missing from our formula for efficiency? Where EFF is equal to E out over E in. So we're missing our energy out. So what is our energy out? Well, if the paint bucket is right here, and the worker is pulling it upwards, we can think of this in dynamics, where it is a force of gravity, mg, pardon me, and there's a force normal. But because the paint bucket is being lifted off the ground, we know that it's moving at a constant speed, so acceleration is equal to 0. So these forces will be balanced, but it has some height that's being applied to it, a height of, which is again 20 meters. And because we know that the height is 20 meters, we can understand that this is going to be gravitational potential energy, because he's moving it up at a constant speed and the forces are balanced. So we can just simply use gravitational potential energy to find out what our true E out is, because E out is just simply equal to EG, because again, there's no acceleration, so the forces are going to be balanced. So the acceleration is 0, forces are balanced, but we also have a height that he's adding, so we can just multiply mgh. Similar to how in the previous lessons we determined how we actually got the formula for mgh, this just kind of applies here. So is equal to EG, which is just equal to mgh. And now we can go EFF. We can sub it in actually. We can go 1, this is 2, 1 into 2. And we can go EFF is equal to mgh divided by energy in, multiplied by 100%, of course, multiplied by 100%. Now from here, just calculator work again, solution. So EFF is equal to 20, pardon me, it wasn't 20 kilograms is the mass, 7.5 meters is the height, but 7.5 meters multiplied by 9.80 meters per second squared multiplied by the height of the mass, because I didn't multiply the mass, 20.0 kilograms. Divide that all by the E in, which is 1.93 kilojoules. What does the kilojoules mean? Well, a kilojoule is basically 1,000 joules. That's why you just put the kilogram, because remember, kilogram is really 10 to the 3. So that's just significant digits, forms of 1. And it doesn't really affect how we really work in this question, because our mass is also in kilograms. So we can assume that everything will just work out fine because of that. But everything's just going to be in kilojoules. So we need to put this into the calculator now. And you will get 7.5 times 9.8 times 20 divided by 1.93. Well, actually, because these aren't in kilojoules yet, you should convert this kilojoules into actual joules, like the constant number, because it will, if you don't, you have to convert everything else, and that's won't work. So we know that it's going to be in actual kilograms, it's going to be 1,000 930 kilograms, because you're multiplying just by 1,000. And now you have, pardon me, 1,930 joules on the bottom. And now you can just put it into your calculator. 7.5 times 9.8 times 20 divided by 1930 multiplied by 100%, and your efficiency is equal to 76.2%. And because there's two significant digits here, we should round off to two significant digits. Our efficiency is just equal to 76%. And that is your final answer. So that is how we determine what our efficiency is. Again, if you want to think about more examples of efficiency in our world, really you can think about like gas-powered cars, because they have efficiency, because they transform chemical kinetic energy into thermal energy. That's how they have a waste of energy. Other things that have efficiency are electric cars. Bicycles even have efficiency. Speakers, everything in our world really has an efficiency to it. And efficiency, again, is just the ratio of useful energy out to energy in. So I hope you enjoyed this video, and in the next video we will be covering power, and that will be the last section for this this unit of energy, and then we'll be moving on to warmth and coldness, heat, and that unit. So I hope you enjoyed the video, and remember, physics rocks.